So since the carry which is generated here will be rippling through the first RCA, so it will take 4 different unit of time the carry to come over here with a delay of 1 unit of time, so 6. So the idea is that first you'll have to generate the carry by the AND function, which takes 1 unit of time, and then it goes through, ripples through the 4 different stages, so 4 unit of time, 1 plus 4, 5, and then it goes through the multiplexer, so another unit of time, so 6. So after 6 unit of time, the carry which is generated here will be coming to the output of the multiplexer. And this multiplexer is, the input is 0 because G is, the first bit is G, so the P0 is Z, so that's why it will be selecting the input from the upper hand. So this value will come over here after 6 unit of time. But for the rest of the cases, all are P is equal to 1, P is equal to 1, P is equal to 1, so this will be now selected to the lower value. So the moment this comes over here, it appears over here, and after 1 unit of time, it comes over here. And now again, this one, all P's are 1, so the moment it comes over here, after 1 unit of time, it appears over here. So effectively, we save time by not allowing the carry to propagate through, to ripple through the rest of the stages. So we are here after 8 unit of times, the carry which is generated over here has been brought over here. And now we will be using the RCA again to basically compute the value, and that's what we get. So the output at the end, what we'll have is we'll have M into T carry corresponding to the carry propagation over here. Then the multiplexer, we have N by M minus 1, that many multiplexer, and their delay, say T bypass or T multiplexer, is right in bypass, you can say multiplexer. So that is the delay associated with the multiplexer delay over here, and then again it passes through the last stage, which is M minus 1 T carry plus the sum which is generated after this, or the final carry, whichever is the max, just like in this case. So it will be T sum or T carry, the max of that, okay? So now you can see that by grouping them into n bits in the form of a ripple carry adder, and by inserting multiplexer to bypass the carry, we save quite a bit of time. Here, for the ripple carry adder, the delay was 17. Here, we find out the delay is 12. So this is how the carry bypass adder works, and this is the worst case example. So the other delays will be smaller than that. If you add some other number where carry will be generated here, you'll find out that the delay will be less than that, because that part and this part will be in parallel. So instead of 7 over here, you'll have less than that. So the worst case delay is the situation where the input carry goes all the way to the output stage. And in this case, that delay is equal to 12. Now, the example shown over here uses m is equal to 4, n is equal to 16. So we can see that bit 03 on the left hand side, 4, 7, 8, 11, 12, 15. Now this is an example which I have included in the presentation material without making any effort to find out if I have to design a good carry bypass adder, is it the right way? Is it the right way to select m is equal to 4 when n is equal to 16, or for any number m, what will be the value of m? Anybody? How do I find out what will be the optimal value of m? Number 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You would take the derivative with respect to m.
Pardon?
You would take the derivative of that equation.
Great.
To the adder.
As simple as that, right? Just differential calculus. So, if I take the derivative of TCBA with respect to m, so this becomes 0, this becomes T carry, this becomes n squared by 2 into T max plus T carry, and the other one will be 0. So if I do this, and in order to minimize the value of the carry, I set this equal to 0. So what do you have? We have 2m squared in this side we will minus 2t carry. So we'll have 2t carry go to this side, and this comes to this side. N by 2m squared T max. Right? Is it? This will be 2 by m squared, right? So this will be this. So we have m is equal to square root of n into T max by T carry. Now we have assumed that, which is of course may not be true depending on how you implement the muxes. The muxes can be implemented by using cascades. You can transmission gates. You can use P transistor and N transistor in parallel to make a switch, and this is say I naught, and here you put P transistor and N transistor. Here I1. So if this is our S, these two will be connected together to S0, and these outputs find out that it also does not have the hazard, static point hazard, which we talked about earlier for that. So the delay associated with this will be different from the delay of the carry, which will be 1 to input, 2 to input NAND gates, because AND OR you can implement as NAND NAND. So you'll find out that if you do the carefully, if you do the simulation, they will be kind of slightly different. But for the sake of our simplification, what we will assume is that Tmax delay is comparable to TAO, or the carry. So which means that n should be equal to square root of n. So when n is equal to 16, you can see that n becomes 4. Now,